So we've reached the last chapter for the semester, chapter 14, Solutions. And this is not the solutions manual to the book where all the answers are. So the first section, we talk about thirsty solutions. I think we all know that you shouldn't drink seawater, right? Like, first of all, why would you want to? Because it tastes horrible. But if you were stranded in the ocean with nothing to drink, it could be tempting, right? It's actually worse for you if you drink seawater than if you drink nothing at all, because seawater is thirsty. It will actually pull water out of your body. Seawater is a solution, the topic of this chapter, and a solution is a homogeneous mixture of two or more substances. So in seawater, water is the solvent, that's the main component, and then there's a bunch of stuff that's dissolved in the water. The primary solute is sodium chloride. There are a lot of other ionic compounds dissolved as well. So we've got sodium ions and chloride ions mixed homogeneously in here with the water molecules. So nature has a tendency towards spontaneous mixing unless that's unfavorable energy-wise. If that causes an increase in energy, then it won't happen. So if we look here, we've got, this could be maybe an aquarium. We've got pure fresh water on one side, and we've got salty water on the other side, and there's a barrier between. If we remove that barrier, we can remove it really, really carefully so we don't stir anything up. If we remove this and we just let the water sit, within a matter of hours, it will have completely mixed, and it'll all be less salty than the salty water, but more salty than the pure water. It'll all be the same concentration. And this is nature's tendency towards mixing. So if you drink seawater, the seawater comes into your intestines, and here's the inside of your cells. This picture is really kind of hard to look at because this part is in your intestines, which, if you think about it, is actually the outside of your body, right? Because you're like a donut, right? So this is really outside your body, and this is inside your body. The cells in your body have water in them, of course, but the water's not pure water. It's a solution. It's got sodium and chloride and all kinds of things dissolved in it. Surrounding those cells are semi-permeable membranes, which can allow some substances to pass and others not. And so these semi-permeable membranes allow water to pass through, but generally sodium and chloride are not allowed to pass through. So this natural tendency towards mixing here, what happens is that the water molecules from inside your body are going to move into your intestines, because if you think of it this way, nature is trying to make these concentrations equal. And since the sodium chloride can't move in this way because there's a barrier, the water will move the other way, and the net result is that your body loses water by drinking seawater. Does anybody have any questions about that? Yes?
It's because it's salty?
Yes.
So another drink that's salty, does it make you thirstier? Like, say you drink Gatorade, but it's not
right.
Like you're using, it's not like you're losing a lot of electrolytes, you're just drinking it.
Yeah, if you're just drinking Gatorade when you haven't lost electrolytes, it's not going to be very good for you. It probably wouldn't dehydrate you because you're already well hydrated. But if you're thirsty, that means you're already a little bit dehydrated. And drinking seawater, the water, your body can't bring any water in from that. It'll just put more out. Gatorade is good if you've been sweating a lot and have lost a lot of electrolytes, because your body does need sodium and chloride and potassium and other electrolytes inside the cells. And when you sweat, you lose some of those compounds. And so the Gatorade is supposed to help you replenish that. So, if you're a football player in August and you're out there practicing and it's 106, yeah, you probably need Gatorade because you're sweating like, oh man, they get so wet, right? Just sweat. they're going to lose a lot of electrolytes. Most normal people doing athletics do not sweat that much, right? So you don't really need to replenish your electrolytes. What you need is water. Water's generally better than things like Gatorade. And then there's the sugar in the Gatorade. And your body uses water to metabolize sugar, and the sugar also can pull electrolytes or pull water out of your body too. So, most people don't really need the sugar either. Anybody else have any questions? So a solution, we typically think of a solid dissolved in a liquid, like salt dissolved in water, and that is a solution. In an aqueous solution, water is the solvent, but you can actually have a solution between any combination of states. You can have two gases, two solids, two liquids, a gas and a solid, a gas and a liquid, etc. And so this table gives us some examples. Solutions are very common around us. The air that we're breathing is a solution. Carbonated beverage is a solution of carbon dioxide and water. Most beverages that we drink are solutions. Metals like brass and other alloys are not compounds, they're mixtures of individual metals. So solutions are very common. So will a particular solvent dissolve just anything? No, which is a good thing because, if you got that solvent on stuff, it would just eat through everything, and that could be really, really bad. So there are limits to solubility. Solubility is defined as the amount of substance that will dissolve in a given amount of solvent. And that solubility depends on nature's tendency towards mixing, and it also depends on the types of intermolecular forces that are present. So let's talk more about this tendency towards mixing. We looked at salty water and pure water in a container. Let's look at two gases. So here is a container with neon gas on one side and argon gas on the other side. If we remove the barrier between them, the two gases will mix together. So most physical systems tend towards lower potential energy. Balls roll down the hill, right? If the ball is on a perfectly flat surface, is it just going to spontaneously roll off to the side? No. And things don't roll up hills either. Yeah.
So it's just going down this concentration rate.
Pardon me?
Going down this concentration rate.
Well, it's a little more complicated than that. So when these two gases mix, does that affect the energy, the potential energy of either gas? No, it doesn't. They still have the same potential energy. Same temperature, same average kinetic energy, doesn't affect their energy. So the formation of a solution, and this is the formation of a solution of two gases, does not necessarily lower the potential energy, so then why does it happen? There's another concept here, and that's called entropy. So entropy is a measure of energy randomization or energy dispersal. It's a tendency of energy to spread out. We can think about entropy in several different ways. A more friendly way of thinking about it is entropy is messiness. Things tend towards being messier, right? It's fall right now and the leaves are falling off the trees. Do the leaves fall into neat stacks? No, they blow all the heck over the place, right? Everywhere. They were very organized when they were on the tree, right? Trees have a very particular pattern of how their leaves are attached to their branches. It was all very organized. When the leaves fall off, they scatter all over the place and they get more disordered, more messy, right? That's an increase in entropy. But what entropy really is the spreading out of energy. So when those leaves spread out, the energy that they have, and they're not at absolute zero, so they have some kinetic energy, their energy spreads out, and that's an increase in entropy. So substances mix due to this pervasive tendency for energy to spread out whenever it is not restrained from doing so. Entropy also explains the transfer of thermal energy from hot to cold objects. So you put a piece of hot, well, like here, I've got this flask, and I've got a hot plate, hence the name, and a cool flask that I'm setting on top of it. And we know from experience that the heat from the hot plate is going into the cool flask. Why? Why is it moving? It's entropy. The heat wants to spread out, and so it will move from a warmer object to a colder object. So that tendency towards mixing caused by entropy is a factor, and then intermolecular forces have a big effect. So intermolecular forces can promote the formation of a solution, or they can prevent the formation of a solution. So quick review of intermolecular forces. The dispersion force is present in everything, and for nonpolar molecules, this is the only type of force that's present. That's where you have a spontaneous dipole that happens in one, it induces a dipole in the next. There's this very brief interaction, attraction, and then it goes away again. With polar molecules, we have dipole-dipole attractions, and this is between dipoles that are always there, permanent dipoles, and so this attraction is always there. Then we have super dipole-dipole force, hydrogen bonding, where the partial charges on these, the dipole moments of these are just extra large. And then finally we have that ion dipole force, which is between a polar molecule and an ion. And so in general, dispersion force is the weakest, and they get stronger as we go off to the right here. So there are intermolecular forces between both parts of a solution or a potential solution. So we have the solvent, and there are interactions between the solvent molecules. We have the solute, and there are interactions between solute particles. And then we also have interaction between the solvent and the solute. And so whether a solution will form is going to depend on the type and relative strengths of those three kinds of intermolecular forces. They could all be the same. They could all be dispersion forces, or we could have three different kinds of forces. And so just as a general rule to help us to predict solubility, we have this catchphrase, like dissolves like. And what this tells us is that if the solvent and the solute have similar types of intermolecular forces, they will probably form a solution. And if they are different, probably not. And we've seen this word before as well, miscible. You can think of that as meaning mixable. Miscible describes two liquids that are soluble in each other in all proportions. You can have a liquid that will dissolve in another liquid and yet not be miscible. Alcohol and water are miscible, so you could have pure alcohol and put a few drops of water in it, it will dissolve no problem. Or you can have pure water and put a few drops of alcohol. You could do any range of proportion and it will dissolve. This isn't a liquid-liquid example, but it's easier to think about. Sodium chloride and water. If you take a pinch of sodium chloride and put it in some water, it will dissolve, right? But if you take a pinch or a few drops of water and put it in a bowl of sodium chloride, is it going to dissolve? No. It's going to get a little bit of it wet, but it's not going to mix, right? But miscible liquids will mix in any proportion. So it's the relative strengths of these forces that determine whether a solution forms. So if we have the interactions between the solvent and solute being stronger than those between each component by themselves, a solution will form. If those are roughly equal, the solution will form. If the solvent-solute interactions are weaker than the solvent-solvent and solute-solute interactions, solution may or may not form, depends on the relative disparity between the strengths. Because even though This is not energetically favorable. It can be made up for by the increase in entropy caused by making the solution and spreading things out. And we'll talk more about that in a minute. This is the sort of question we should be able to answer. Determine whether each compound is soluble in a hexane. So what we're thinking about here is like dissolves like. We're looking for compounds that will have intermolecular forces similar to those found in hexane. So what's hexane? What are the two elements in it? Carbon and hydrogen, right? This is a hydrocarbon. We learned that the anes, there's methane and propane, and the prefix in front tells us how many carbons, and the ane tells us they're all single bonds. So we should be able to draw a structure for hexane. We don't actually need to, though. These are carbon-hydrogen bonds, and I told you that I expect you to remember that carbon-hydrogen bonds are nonpolar. So all the bonds in hexane are nonpolar. Doesn't matter how it's put together. If every bond is nonpolar, this is a nonpolar compound. Okay? So this is nonpolar. So for something to dissolve in hexane, it will also need to be nonpolar. Is water nonpolar? No. Water is like one of the most polar things that you can get. So this is polar. It has hydrogen bonds, and it's definitely not going to mix with hexane. How about ammonia? So it's like, we're not really sure. So we've talked about ammonia, but not nearly as much as water. Let's look at the Lewis structure for ammonia. You see that lone pair there? So we have a lone pair here. I know it lags behind, so sometimes it's like, no, actually it's not showing yet. There's a lone pair in the central atom. If there's a lone pair in the central atom, the molecule's polar 95% of the time. What about the other 5%? You can have something like an expanded octet where you have 4 lone pairs and 2 bonding pairs, and that's going to be linear and nonpolar, even though it has lone pairs in the central atom. So it's definitely and you can also have that with a trigonal bipyramid where you have 3 lone pairs and 2 bonding pairs. You can get a linear molecule. But those are pretty unusual. And I won't ask you questions like that on an exam because that's mean. And, contrary to popular belief, I'm actually not a mean person. So, No, the odd or even number of electrons doesn't matter. Because for most compounds, when they bond, they end up with an even number of electrons. And it doesn't really matter who brought the electrons. We're just looking at how they're distributed in the molecule overall. We're looking for symmetry. So when we have a lone pair, that means it's not going to be symmetrical. It's going to be lopsided. And of course, this is a fast and easy rule of thumb way of predicting polarity, but I think it's just so much easier, and it works almost all the time. And for the other times, we can get into the details, and we don't need to worry about it for this. So this one's polar. Is it going to dissolve in hexane? No. How about propane? Yeah. See, propane is a lot like hexane. If we wrote out the formula for hexane, it's going to be CH3, CH2, 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 CH3. They're very similar, right? Just carbons and hydrogens. And so they have very similar forces between them, so they will mix together. So this is nonpolar. And this will dissolve in hexane. How about hydrogen chloride? That's polar. So this is a diatomic molecule. There's only 2 atoms. It means there's only 1 bond. If the bond is polar, the molecule's polar. And my shortcut rule of thumb is if these are different nonmetals, except for carbon and hydrogen, I expect you to tell me this is a polar bond. Polar bond, polar molecule will not dissolve in hexane. Any questions?